started my company about a year and a half ago, really looking to apply technology to new materials. And so some of it's centered around that. Some of it's just sort of the history of making and how we've evolved and how we make things. So like 100 years ago, the advances of computing were really about making things automatic for us. So really taking very manual processes and turning that to something that was automatic. And the next thing was really about making those processes flexible. Like the first computers, they weren't very flexible. They were very mechanical, and you had to totally reinvent them just to change the computation. So we got to this stage of the flexible type computer. After that, it was sort of accessibility, really getting those out into the world on a massive scale. Not just into people's homes, into businesses, everywhere. That was kind of a really important part where the computation started to take off. And then the last one was the sort of ubiquitous cloud model that we have now, which is really about taking those computers and making them accessible everywhere. And from your home personal computer to your smart devices, but it's really connecting to much more horsepower sort of on the back end. But really, that's just a bunch of hardware hiding away somewhere. We all know that it's still connected to something out there. So kind of putting that in context of devices that make. So they've gone through the same process. The sort of automatic process to start, so where we took automation and applied it to sort of handcraft type things. The machine on the left is an old stamping machine that make automotive panels. And so before that, people were just banging these things out by hand. So, we took that and made all that automatic. And then we added computers onto that, really old jankety computers like the one on that very early CNC machine. And to make that process a little bit more flexible. But they were still very hard to reprogram. There was technology hiding away, in labs and things like that. It wasn't something that people really saw out in the world. And more recently, it's kind of shifted to this accessibility. And so, how many people here have a 3D printer on their desk or in their office or something like that? Look around. I mean, that's a pretty good chunk of you guys. So we're kind of at that point, sort of in that area over the last, I'll say, decade or so, where we've taken that sort of power of making stuff and putting stuff in the real world and making it accessible to a lot of people. And it has a lot to do with patents expiring on 3D printing, and there's thousands of 3D printer companies now making all sorts of different technologies that they can stick on your desk for literally a couple $100s. We could probably order one live on Amazon right now and have it here by the end of the show. So being able to get that out in the world is really important. And then the next stage of that is sort of this cloud manufacturing, which is just in its infancy now, just really starting to get out there where you can upload your data, CAD part, whatever, up to the cloud and get a part back. And that's really kind of the next stage of evolution of all this. And the reality, though, is that looks like that. There's just like the computer hardware, there's a whole bunch of hardware sitting away in a shop somewhere that's connected to all those computers and interfaces and all that other stuff that can get you those parts. I'd say we're somewhere kind of in between these two things right now. We're not really at the ubiquitous stage yet. We're still on the sort of accessibility stage. And that accessibility stage is that's not just the stuff that's on your desk, that's really also just the accessibility even to smaller companies and industry. Computation's really made that stuff much less expensive and accessible to all sorts of industries. So one of the big advances, especially over the last 5 years, has really led to the speed increase in how people make stuff. So 3D printing on the left, that's a 20-minute print. The CNC on the right that's really, it doesn't look that much different than you might have seen 30 years ago, but they've actually gotten a 50 to 100x increase just from computational power, a little bit of metallurgy, and the computation on both the software side and the hardware side. So all that stuff put together has led to these massive increases in how we make stuff in all sorts of industries. And so a little more focused on kind of where my company's going. So right now, a lot of those advances have happened so far with metal solid parts and plastic solid parts. And 20 years ago, you had to be still a pretty mass manufacturer to get any good ROI out of making anything in those spaces. So let's say 20 years ago, to be able to do some injection molding in plastic parts or manufacture anything out of metal, let's say casting or even machining, you had to be doing a lot of it because the programming took a while, the setup took a while, like all of those steps to getting to that part took a really big chunk of time. And so what happened was in those last 2 decades, we've kind of flipped that equation using data computation and applying it both to hardware and software. And it's kind of gone, at least on the plastic side, from these big honky machines, kind of like the old servers, if you will, in that analogy, to the sort of desktop machines. And not everything can fit on a desk. Some of these 3D printers are still the size of this table, but it's still gotten much smaller, much cleaner. You can stick it in an office and be making and really manufacturing parts almost anywhere. So it's kind of flipped that equation, and that was faster and could really only do one thing. This is slower, but can do a ton of different things. And so it kind of filled in the gaps on sort of the prototyping and low volume production. So like if you want to design and create a new product, it's far easier. The barrier of entry has been lowered immensely just in the last 2 decades. And where my company's focused, though, is the top row, which is metal sheet. So sheet metal is in all the products. You guys have spec'd it for all sorts of stuff in architecture. Automotive is obviously a major. There's 100 million cars and trucks and buses made last year alone, okay? It's a staggering number. And most of those are made out of formed metal sheet. I'm sure most of you took a car or airplane or something to get here. It's all made of that kind of stuff. Consumer products as well. The thing is with most of the forming that goes on in automotive industry, aerospace industry, that really we're at that step, the automate step. It hasn't gotten to this sort of flexible and accessible and ubiquitous step yet because the barrier to entry into that is really high. And most of those parts are made with pretty simple dies, but they're very expensive. For something for like an automotive fender or hood, those dies can be upwards of $1 million, $2 million, take a year to produce. So for other industries like architecture, it's very hard to make the math of something like that production method work. Even though it's a production method that's been around for a century, it's not something that's accessible to a lot of industries. And still kind of a very slow method even in the automotive and aerospace world. So our concept is around making hardware that kind of flips that equation, much like 3D printing did for plastic and other metals. So the idea is, to be able to get parts quickly, no upfront investment in some kind of dies or tooling or things like that, and really just be able to create parts on the fly on demand. Yay. Okay, so this is a prototype that we've been working on since last year. Hopefully it'll load in a second. But so this is our sort of smaller scale proof of concept on metal 3D printer when it loads up. But the concept is that you can go directly from your CAD or digital data directly into a manufactured product. So this has been in development since last year. This is really, as we're kind of going out and proving out the technology, this is one of our test beds. But really the idea is that you can make the technology available quicker and easier for prototyping in industries that are already using it, stamping and things. Oh, there we go, nice. Industries that are already using it, but also make it accessible to people in other industries such as architecture and construction. So this is kind of a smaller scale prototype. Again, we're looking at all different industries, but these are all directly made from a CAD file using some new methods that we've developed. So one nice thing about this, it's much faster than traditional 3D printing. We're actually forming the sheet metal on the fly. And there's been some research into this over the last 2 decades. We've developed kind of a new take on it. But one of the big takeaways here, it's much faster than actual additive printing. The concept is that because we're just manipulating the metal into the shape, so we like to say about 100 times faster than traditional additive, although as we get into larger machines, we think that multiplier is going to go up quite a bit even. I have a couple examples in different industries here. This is a architectural metal panel that was a prototype for a project. But basically, again, so as we go from an automotive part to a architectural part to things for any other industry, it's really about, as we're switching from part to part, there's no change in tooling or anything like that. So the flexibility of that manufacturing, I think, is what's key, and that's really the next run of machines that'll be coming out, and not just by us, but all sorts of different industries. That's really the key to making them work well. This example here was for a fin for a wind turbine, and actually, these things aren't really made out of metal. One of the other applications that we're going to be using this for is actually for molds for composites and other materials. So in architecture, using it for molds for FRP and concrete. In this industry, it will be for carbon fiber. The concept is, though, that we can create not just the direct materials, but very inexpensive formwork for other materials. Okay, so that kind of gives you an idea of surface quality and things like that. We're getting close to Class A automotive right now, so exterior kind of finished work, certainly within tolerance for most building and construction projects. And this method makes no noise or sound or anything like that that you'd typically find of heavy stamping processes. So it's much more, while it's not something you'd probably have on one of your desks in the office, it's still something that's accessible to much smaller and flexible shops. So we kind of put this in a category that's sort of direct manufacturing, right? There's no sort of intermediary step of making a mold or a die or something else to create your final product. And I think we're going to see a lot of that. We've seen in the architecture industry, for instance, like concrete 3D printers, right? You used to have form work to make that concrete. Now we're directly forming that. There's a number of companies exploring those options. But this kind of direct manufacturing concept of going right from the CAD files that you guys are all making and working on into the part is kind of the important takeaway. I'm going to kind of skip this. One of the things we've designed, though, is it also, the way it feeds the sheet metal back and forth, it's kind of ready for automation. That's kind of another big key as we move to this sort of ubiquitous concept of computing, is that whatever you're doing has to be able to be automated. It has to be designed that way to be automated from the beginning. Let's see, I already touched on, it's much faster than additive. You can get to your first part right away, very quickly. We're targeting a lot of different types of industries here. But in all of them, it's really about hitting it from a couple different sides. One is the prototyping and low volume. The other is on the production side. We've done some studies with an automotive manufacturer where we can actually produce parts in high enough volume that they can get rid of their dies altogether. So that's one of the directions we're going. And of course, repair. So on-demand sort of parts after products are out in service. It's always a big deal. It's less prevalent in the architecture world, but automotive accidents happen all the time. So to make those replacement parts a decade or two after you've made the original thing is actually very expensive for the manufacturer to kind of keep that going and retool themselves. So it's kind of one of the other focuses of ours. I'm going to skip that. We talked about the architectural applications. Again, this whole concept is going to be scaling up to architectural size items. I think that's one, important comps. Right now, 3D printing is very small in general. To get any significant scale, you have to kind of change your methodology of how you're doing it. So to produce something that from the get-go can make something at scale is critical for other industries to adopt. Whoa. Let's see. It's aerospace application. This was for a replacement part for something in aerospace. Again, very, very expensive to retool and get things up and running for these guys, so being able to direct manufacture is key. And we see this as kind of, there's a lot of talk right now of sort of these micro factories and how do you create small flexible factories. So we're working with 2 robotics companies to kind of figure out how to integrate that into a small production line. So something like this would normally be the size, to produce that part would be like the size, not just this room, but maybe 4 or 5 times the size of this room, all the hardware and stamping and that whole line. So really changing that to a much smaller, flexible concept. And the thing is, all this stuff sort of upstream of our process is already available. All the stuff downstream of our process is actually already in production. So it's the kind of, our thing in the middle that we see as the key to that working. And the prototype that you saw is a small sort of, I'll say, I don't want to say desktop printer because it weighs about 300 pounds, but it can sit on a desk if your desk can support it. The larger scale version that we're working on now in prototyping is approximately I think the text got messed up there, but it's for approximately 4-foot width panel, and reasonably we can do about a 3-meter long panel through that machine. Just kind of more stuff on the prototype. And of course it adjusts to different widths and things like that. And I kind of wanted to end on this, you know, just to put it in perspective. So this started as a garage startup. The whole prototype, everything we've done in-house. And, you know, I think technology is always, it's contextual, but it also, it has to fit into like a particular time period. We couldn't have done this 10 years ago, probably not even 5 years ago, just because the accessibility of the various tools from 3D printers, CNC mill, FEA analysis, all that kind of stuff. You know, 10 years ago, the software alone would have been $100,000, and now it's practically free. 3D printers, again, you can order one on Amazon, have it at your house tomorrow. You know, so all of that kind of stuff makes this possible now. And I think we're going to see an acceleration in all these types of tools that we're using to make stuff because all this hardware is so accessible. I think that's it.